Hello everyone, today we're going to look at exponentials. The most basic form of an exponential is y equals b to the x. X is the exponent and b is the base. We do have a few restrictions on the base. They are that b has to be greater than 0 and b cannot be 1. So we're going to look at why this is. First of all, if b was 1, then we would have y equals 1 to the x, but 1 to any power is 1. So we wouldn't have an exponential, we'd have the line y equals 1. So that's why y cannot be 1. B cannot be 1. We want b to be greater than 0 because we want our function defined everywhere. And if b was something that was negative, say negative 2, and I raised it to the 1/2, 2, that would not be defined because remember the power of 1/2 means the square root. And this would be an imaginary number, not a real number, which is what we want. Okay, so we want b to be positive so that b to the x is defined everywhere. And we don't want b to be 1 because we want an actual exponential and not just a line. So let's recall the rules of exponents as we do out a couple. Let y equal 3 times 4 to the x and find the value of y for the following values of x. X equals 2. We have y equals 3 times 4 squared. So we need to remember order of operations, so PEMDAS. Exponents come before multiplication. So 4 squared is 16. And then we do 3 times 16, and that's 48. What about x equals negative 2? So y equals 3 times 4 to the negative 2. Now we have to remember what a negative exponent means. You learned about negative exponents back in Math 110 or 100 or 105 or one of those versions that you took. And it's coming back to haunt you now. So you need to remember that a negative exponent means I'm taking that power, that base to that positive power and putting it in the denominator. So 3 times 4 to the negative 2 is 3 divided by 4 to the positive 2, which is 3 over 16. What about x equals 1/2? So we just talked about this. Whenever I have the power to 1/2, that means the square root. Now remember, in general, x to the 1 over n is the nth root. So 1 over 2 is the square root. We don't write the 2 because we know it's understood. It's the one we use the most. Okay, so this is 3 times the second root, but that's just the square root. Square root of 4 is 2, so we have 3 times 2, and that gives us 6. And then let's combine the two. X equals negative 1/2. So I plug in 3 times 4 to the negative 1/2. So again, the 1/2 means the square root. The negative means I put it in the denominator. And I get 3 divided by the square root of 4, which is 3 over 2. Now we're going to look at the graphs of exponentials. So we're going to have 2 of them, and we're going to compare and contrast the 2. So on the left, we're going to do y equals 2 to the x, and on the right, we're going to do y equals 1/2 to the x. Whenever you don't know what a function looks like, you want to make a table. So I've got 2 tables set up here as well. So I'm going to start with the easy one, which is when x is 0. Remember that any base to the 0 is always the same thing, and that's a 1. Then I'm going to keep going down the table. 2 to the 1 is 2. 2 squared is 4. And 2 cubed is 8. So hopefully we agree with those. And then I've got the negatives. Remember that the negatives just mean 1 over the positive power. So 2 to the negative 1 is 1 over 2. 2 to the negative 2 is 1 over 4. And 2 to the negative 3 is 1 over 8. Okay, so I've got the same ones that I had before in the positives, just now they've been reciprocated. They're now in the denominator. So when I go to graph these, I've got, let me see if I can do some dots here. 0, 1, 1, 2, 2, 4, close enough, and 3, 8. And then going to the negatives, I got -1 comma a half, and then the other ones are getting really, really close to 0. And when I connect these, I will be getting something that looks like this. Okay, so there is y equals 2 to the x. Now we're going to go over and look at y equals 1/2 x, and again we're going to compare and contrast the two. So again, we'll start with 0. Anything to the 0 is 1. 1/2 to the 1 is 1/2. 1/2 squared is 1/2 times 1/2, which is 1/4. And 1/2 cubed is 1 cubed over 2 cubed, so I get 1 over 8. And then again with the negative exponents, it's the positive exponents but flipped. So 1/2 to the -1 is 2. 1/2 to the -2, is 4. And 1/2 to the -3 is 8. And then again when I go to plot them, I always have 0, 1. I'm going to fix that. Close enough. 1, 1/2, getting really closer to 0. Those are close enough. And then -1, 2, -2, 4, and -3, 8. And then again, we want to connect to them. And we're going to get something that looks like this guy. Well, it's a little off. Maybe we'll redo that. There we go. Okay, so there are a couple of things that these graphs have in common and a couple of things that are opposite, and we're going to go over those. So one thing they have in common is the point 0, 1. So again, as long as we're not multiplying our exponent by something and we're not adding or subtracting it, we're always going to have 0, 1 because anything to the 0 is 1. So that's something they have in common. Another thing they have in common is they both have an asymptote at y equals 0. And that just means that as I go off to either positive infinity or negative infinity in the x direction, my y values get really, really close to something. And that something is y equals 0. Okay, so y goes to 0 in one of the directions. And again, that's called an asymptote. And what that tells me is that if I kept going in this direction, I get smaller and smaller numbers. 1 over 16, 1 over 32, 1 over 64, 1 over 128, getting really, really close to 0. And the same is true in my other graph if I'm going more further in this direction. X equals 4, x equals 5, x equals 20, getting really, really close to 0. But I never actually hit 0, right? If I have a positive number and I'm multiplying it by itself, I will never actually hit 0. So that's something to keep in mind. All of my numbers are positive. It never crosses the x-axis. Okay? So we've got, it goes through 0, 1. It gets closer and closer to 0, but never hits it. It's always positive. Those are what they have in common. And hopefully we can see the major difference is that my first graph is increasing and my second graph is decreasing. So y equals 2 to the x is going higher and higher, where y equals 1/2 to the x is getting smaller and smaller. This has to do with b. If b is bigger than 1, then y is increasing. And if b is between 0 and 1, remember it's never negative, and it's never equal to 1. So it's either greater than 1 or it's between 0 and 1. And if it's between 0 and 1, then my function is decreasing. Okay, so that's something to keep in mind, whether it's graphing it or in an actual example, which we're going to do next. So we're going to do some examples using exponential functions. And really this is just an exercise in can you plug things into a function correctly, and can you do the math correctly, either knowing order of operations or plugging it into your calculator. So the first one, the number of bacteria growing in an incubation culture increases with time according to B equals 2600 times 4.8 to the x, where x is in days. Find the number of bacteria in 0 and 10 days. So for 0 days, I plug in 0 for x, and then I remember that anything to the 0 is 1, and then I have 1 times 2600, which is 2600. So we're starting with 2600 bacteria. For 10 days, I plug in x is 10. Remember, order of operations, we'll do 4.8 to the 10th first. We get this really large number, and then we multiply it by 2600. My calculator gave it to me in scientific notation, so 1.688 blah 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 times 10 to the 10th. And in a calculator, sometimes you'll see this as e to the 10, or you'll see a very small 10 up in the corner. So this is a very large number, and if you remember how to do scientific notation, that tells me that I'm moving the decimal 10 places to the right. And I get this lovely guy, and if I add in commas, I can make sense of this a little bit more. So 16,880,516,150, a very large number. As another example, a population is decreasing by the following function, where t is in years since 2010, and then of course I did the wrong variable. So xt, we'll pretend it's the same variable. P equals 15,000 times 0.95 should be t. Find the population in 2015 and 2020. So notice it says the population is decreasing, and my b is 0.95, so that makes sense. B is less than 1, so I know it's a decreasing function. I know it's going to look something like this. Okay, and that's again because b is less than 1. So find the population in 2015 and 2020. Remember that the variable is in years since 2010. So 2015 is 5 years since 2010. So t is 5. So p equals 15,000 times 0.95 to the 5. I want you to plug this into your calculator and make sure you're getting the same answer if you haven't been doing this already. So 15,000 times 0.95 to the 5 is 11,606.7, but it's a population. You can't have 0.7 of some living thing, so you round. So it's 11,607. For 2020, that is 10 years since 2010, so t is going to be 10, and we plug it in. Now I know that my function's decreasing, so my answer had better be less than the 11,607 I had earlier for t equals 5. And I do it, and I get 8,981.05. Again, we round to the integer because it's a population, and it's 8,981. And my values did go down, so that makes sense. Okay, so make sure that your answer always makes sense, that it's either increasing when it's supposed to or it's decreasing when it's supposed to. And make sure you read through the book and try out any practice problems, and let me know if you have any questions. Thanks.